industry since leaving school, so that was quite a few years ago now. Done various roles within the industry, being a service technician, being a contracting engineer, worked as a technical engineer for a wholesaler, and now Danfoss for quite a number of years. Today we're going to go through all of the questions that were asked during one of my recent webinars on Cold Room Defrost. Now, the webinar itself mainly focused on electric defrost, please feel free to ask more questions from today, and I'll do my best to answer them as best I can. Might even use a whiteboard behind me, to try and be a bit more graphic and explain things. A few things I've got to mention. On the 7th of July at 1 p.m. CET, a very good colleague of mine, Jens Andersen, is doing a live webinar, live broadcast on refrigeration basics. So that's the 7th of July, 1 p.m. CET on YouTube. I'm sure my good colleagues are putting the links on the screen as we speak. So that's that. So as I said, I gave this webinar earlier this week on Tuesday. Did 2 sessions, one in the morning, one in the afternoon, and it was all about the defrost, and mainly we focused on electric defrost, and we had quite a few sort of questions that were answered. And basically, what I'll do during this event is I'll read the questions and try and give an answer. If I can see some friends of mine are joining already on the chat, so nice to see you. And if you've got any other questions, what I'll do is I'll sort of discuss the chat that that we have on the screen, so I can see the questions that are coming in, and then I'll also go back to answering the questions that were asked during the webinar. So we'll sort of flip between the two, and as I said, maybe use the whiteboard a little bit. So first question that were asked during the webinars that I did, and a very interesting question actually, said, is there any extra consideration regarding defrost for CO2 applications? Basic answer is not really. CO2 is still a refrigerant. I guess the biggest challenge with CO2 is obviously the working pressures that we're talking about, considerably higher than what we're used to, I guess, with traditional refrigerants. We've got to bear that in mind. One thing that I would say is with CO2, as you should with all refrigerants, would be to pump out the evaporator prior to defrost. And I guess for CO2, that's ever so important because of the pressures that we can reach. We're going to put a lot of heat into that cooler. So that was that one. Somebody asked a question regarding ATEX or hazard applications for defrost heaters. Not something that I've ever been involved in, and to be honest, that would have to be taken with the evaporator manufacturer. A bit of a interesting one. Never been in cold rooms that are in an ATEX area. But if anybody on the call has got any experience, please put it up on the chat and we can have a discussion. Next question was, what is the amount of heat required for defrosting in regards to the cooling capacity? Any factors, any rules of thumb, things like that? Again, this is very application dependent, and I've had a chat with a few evaporator manufacturers, and basically they either wouldn't tell me or there isn't a rule of thumb. Basically, they said that they decide the amount of heat depending on the size of the cooler, the evaporating temperature, all of that, but they couldn't or wouldn't give me a rule of thumb, which is a shame. I have seen some figures from quite a few years ago, and that mentioned around about 130 watts per sort of cubic foot, which is sort of that sort of size. Don't know how true that is. I'm going to try and get that clarified a little bit further. During the webinar, I did a slide on adaptive defrost, which is a functionality that's built into the Danfoss Adaptable range of controllers, and somebody said, what platform is that on? Basically, something like the AKCC 450, 550, the new 55, 740, they have that functionality. but to have the true functionality, it does all need to be connected to a Danfoss front end. What I would say is, please contact your local Danfoss sales office, and I'm sure my colleague will put that link in the chat, and take that sort of discussion with your local Danfoss sales office. Yeah, similar sort of question. Is there any usage ratio between defrost heaters and hot gas practically? What you can sort of say is that hot gas generally is more efficient, definitely more efficient. It doesn't take as much time because we're actually, if you think about the electric defrost heaters, we have to heat up the coil, so the pipes and the fins and the ice from the outside. Whereas when we use hot gas, we put hot gas into the tubes within the evaporator, so that's instant. That goes where the heat goes, where we want the heat very, very quickly. So generally, hot gas defrost a lot quicker. Yeah, cheaper because we're not using electrical energy to power the heaters. Obviously, some sort of downsides is we need different control methods, control valves, depending if it's 2-pipe, 3-pipe, things like that. If the question was regarding, is electric defrost more common than hot gas? I think a lot of that depends on the application. If you're talking small commercial cold room, then it's electric. If you're talking large industrial applications, then everything is hot gas defrost. Then you've got the let's say heavy commercial, light industrial, as I call it, which might be electric defrost, might be hot gas defrost. It depends, but it is an interesting question. Then during the presentation, I was trying to give reasons why you get frost on a coil, and one of the causes is a low refrigerant charge. Now, if you have a low refrigerant charge, you have a low suction pressure or a lower suction pressure. So that would, if you've got a lower suction pressure, the TD on the evaporator, so the difference between the evaporating temperature and the air off temperature increases. So for every amount of air that passes over the coil, we actually take out more moisture. So we have more moisture on the coil, which more moisture equals more frost. So that was that one. I'm just keeping an eye on the chat here. Okay, let's break off a little bit and have a look at the chat. Yeah, lots of nice comments so far. Greetings to everybody, that's very nice. Hi, basic question from Herman. What's the recommended temperature to install a defrost system? Well, every cooler needs a defrost system, but if we're talking positive temperature, so above 0, generally it's off cycle. So we don't use defrost heaters, we don't use hot gas, cool gas, things like that. Generally in that off cycle period, when the cold room is down to temperature, the refrigeration system shuts off, the fans on the cooler keep going, draw that air over the coil which is above freezing, and just the action of that air will melt any, let's say, frost or rime, as we call it, on the cooler. As soon as you go negative temperature, so below freezing for the room itself, then you would need a defrost. And as I said, the most common would be electric defrost. It all depends on the application, duty of the equipment, number of coolers, so on and so forth. So I hope that answers the question, Herman. I don't know whether you were in the webinar that I did on Tuesday. You can access the recording of that webinar, and I go through basically the reasons for the frost and how to set up the electric defrost and termination temperatures and all of that. So if you need all that, then please go and watch the videos of that webinar that I did. Okay, another question's come in. Some more questions coming in from Stanley. What is the ratio of cooling time, defrost time, let's say, for a blast freezer? Yeah, well, if we're talking blast freezer, and the idea of a blast freezer is that we load that cold room up with product. and then we blast chill or we blast freeze that product in might be a 30-minute duty cycle time, it might be an hour. Generally, what you would do in that scenario is that you would run that blast freezer or blast chill for, let's say, 1 hour or 2 hours or whatever that duty cycle is, to take the product from the entry temperature to the required leaving temperature, and then you would defrost the coil. If that blast freezer is running 24 hours a day, 7 days a week, so you load a blast freezer with product, blast it down to temperature, empty it, then put another load in straight away. You really need some time between those loading of the blast freezer to actually carry out the defrost itself. So I hope that answers that question. If it's a general freezer room, generally 4 times a day, start off 20 minutes to 30 minutes sort of maximum defrost time, but then terminate the defrost on a termination temperature. So I hope that answers that, Stanley. Athnan asks a question: how much time is needed in defrosting generally? I think I've just said that. Sort of 20 minutes is a good start point, maybe to 30 minutes. But if you can have a defrost termination stat, then you will terminate defrost when that coil is, hopefully clear of ice. Termination temperature, start off round about sort of +4, +5, maybe go up to +7. If you need the termination temperature any higher than that to clear all the ice, then we need to look at the overall defrost functionality, the time, the number of defrost heaters, moisture, airflow, all those sort of topics. Okay, so that's the questions on the chat for now. I'll just go back to the questions on my screen from the webinars. Thank you. Somebody said, can we put extra heaters or replace existing heaters with, let's say, more powerful defrost heaters into the evaporator? Again, sort of, you would have to have a discussion with the evaporator manufacturer. Best thing to do really is to make sure that all those heaters are actually functioning and working, and the easiest way to do that is put an amp clamp on the heaters and make sure that they're drawing amps. Each evaporator is made with a certain number of holes within the coil block itself where you can put the defrost heaters in. So long as they're all full, then that will have the maximum number of defrost heaters as suggested by the evaporator manufacturer. So you can't put any more in because there physically isn't space. I have seen people put defrost heaters on the face of a coil just to sort of give it that extra bit of a boost. And what we'll try and do with my beautiful whiteboard, hopefully everybody can see it a little bit. If we think of our evaporator, so there's our evaporator. This is the let's say the back side, so the air on. You've got your tubes going through your evaporator like so. You've got your fins on your tubes like so, and your defrost heaters are actually sort of within the coil itself. What I've seen people do is a bit Heath Robinson, but basically strap a U heater. That's not the greatest pen in the world, but basically strap either 1 or 2 U defrost heaters onto the face of the coil if there's a lot of moisture, a lot of frost building up on that face. Okay, any more questions come in? No, not so far. Okay, so that was that one. Somebody said, is there a quick fix method if the defrost heaters are not working? Unfortunately not. You need to take that heater out. What I've sort of scribbled on the whiteboard there, I suppose it's a quick fix to add extra heat to the coil, but it's not perfect. You're much better replacing the faulty defrost heaters. Vanda, you've asked me a very strange question. I don't know whether that's meant for me or not. something about fruit bats. Yeah, not sure on that one. Okay, a good question has come in from Abhijit. I hope that's near enough for close pronunciation. Can we generate auto alarm when heater fails? Yeah, I guess you could. I mean, every electrical heater pulls a certain amount of amps. You could monitor the amperage that's drawn from the feed that feeds those heaters from the defrost contactor with a CT device. And yeah, if the amperage drops, yeah, I'm sure you could generate an alarm. I don't know that functionality built into any sort of standard piece of kit that we can buy in the market today, but I know there are companies out there who do a lot of energy monitoring and alarm on that. So yeah, that would be one way to do it for sure. Good question, actually. Okay. Somebody said, and this is quite an interesting one, what is the freezing pattern of an evaporator when it's low on charge? Now, I'm going to try and use the technology that I've got with me, and let's see how well this works. I'm just going to try and share my screen a second. I'm going to try and share screen 1. So that's what you can sort of see, but let's go to that presentation here. And maybe I've got a picture, maybe I've not got a picture. Let's put that one up. I don't know how well this will work. Let's see. No, that's the wrong screen. So let's change the settings over. This is like car crash TV, I think. So hopefully you can see that screen now. That's basically an overview of an evaporator within a cold room. And here we're looking at the side of the evaporator. We've got 2 expansion valves, 2 distributors or spiders, as they're sometimes known, suction. Now, generally, if the system is short of gas, the spiders and the distributor legs, they will ice up quite quickly. So that's a sort of a very good visual indication of charge. But obviously, the most important thing really is to check your suction pressure against where it should be. But if you want a visual indication on your cooler, then the distributor legs are a very good place to go, because you'll get frost and ice build up on those, but you'll get nothing on the coil itself. So that's a sort of good one to look at. So if I can then stop sharing. See how this works. All right, so then hopefully we're back to there. So hopefully you can see me on the camera again. That's good. Right, let's see what other questions we've got. Is there anything else you recommend installing other than a liquid separator to protect the compressor for hot gas? Hot gas defrost is very good. It's very energy efficient, but with it comes, let's say, challenges. And depending on the size of the system, depending whether we're talking IR, industrial refrigeration, or let's say commercial refrigeration with hot gas, we still got to be very careful because we are pumping hot gas into an evaporator. And you can get things like liquid shock, because, suddenly that evaporator was, I don't know, let's say evaporating at -20, and then all of a sudden we're going to put hot gas into it, which might be at 70, 80. So we've got thermal shock to take care of. So that's sort of one thing that we need to be aware of. But a liquid separator, yes, it is incredibly important, because depending how we do the hot gas, whether it is reverse cycle, whether we're literally taking hot gas from the discharge line, dumping it into the expansion line on the cooler, we could get liquid back down that suction line. So a liquid separator is extremely important. And the other thing to say is that liquid separator has to be sized suitably for a system working on a hot gas defrost. So yeah, that is important. Anything else? I mean, we could probably spend at least 2 hours just talking about hot gas defrost, but we really need to make sure that the control scheme for the system is working and it works well and everything is correct. We need the appropriate, we've got to empty the cooler, we've got to make sure we have lots of drain down time. Yeah, there's so much we could sort of talk about, and maybe that's a topic for another webinar, as somebody did actually suggest on Tuesday. So I hope that sort of is a good answer to my friend at the engineering mindset. Dwayne says, gas charged or liquid charged expansion valve, which is more efficient? Not too sure by what you mean by that, Dwayne, but basically an expansion valve is the charge in the bellow of an expansion valve is a mixture of components. I'm not going to say refrigerants, it's got some of that, but it is a mixture of components that suit that application for that expansion valve. So maybe what you're appertaining to is the actual type of charge that we have in the expansion valve. Let's say an MOP charge, for example, where we don't have a lot of, let's call it a substance inside the file, so that if we have a very high evaporating temperature, then we don't open the valve anymore, so we protect our compressor from a high suction pressure. So maybe if you want to expand on that question a little bit, I can try and answer it a little bit more. Abhijit says, can we design one-to-one indoor, one outdoor unit for hot gas defrost? Can we use hot gas defrost for small units? Yes and no. What I'll do is I'm just going to share my screen again. So just bear with me while that sort of flips over, and I'll try and sort of explain that the best I can. So let's go back. I'll put up another one of my beautiful sort of presentations. And again, you have to bear with me a little bit. There's this is just a sort of general collection. So they're not very polished, let's say. The slide that I've got up on the system now basically shows an incredibly simple hot gas setup. Now, this system has some challenges. We've got our, compressor discharge through the condenser, liquid line, solenoid valve, expansion valve, evaporator. Then we've got a crankcase pressure regulating valve, or it might be a evaporator pressure regulating valve, and that's the sort of normal operation. If you want to do something very, very simple, you can take a tapping off the discharge line through a hot gas mag valve or solenoid valve that basically feeds hot gas into your expansion line just after the expansion device. Should really have a check valve, and then it will go through the evaporator, heating the evaporator up and melting, ice, frost, etc. Challenge is that's a one-to-one system. So we get a sort of ever reducing amount of hot gas because we're putting hot gas into the evaporator here. It's condensing back to a liquid. We're not really going to put a lot of vapor back to the compressor. So in essence, the system runs out of hot gas. It's okay for a very quick, short burst of hot gas to the evaporator, but you will eventually run out of hot gas because you're not getting any vapor back to the compressor to compress, etc., etc. The other bigger issue is the risk of liquid slug back to the machine. Now you can see here we've got a nice big suction accumulator or slop pot, as I've called them in the past, and that hopefully protects our machine against liquid because a compressor is a vapor pump, it's not a liquid pump. It can be mitigated by the use of what's called a re-evaporator coil. So sometimes you have one evaporator and then you might have what they call this re-evaporator coil to boil off the rest of that liquid, and then we get some vapor back to the compressor. So yes, if you ask me, would I install it? Then not really, because it would run out of hot gas. Really, for a proper hot gas system, you need at least, in a medium temperature system, you need at least 2 evaporators running and 1 on defrost. And then if it's a low temperature application, you need at least 3 evaporators running and one evaporator on a defrost to actually generate the amount of hot gas required to melt that evaporator. Now, you might argue, and I'll try and find another picture somewhere in here, and there might be a little bit of lag, so apologies for that in the system. This is something that's used on transport refrigeration. Now, this is a one-on-one system. This is used on the, a reefer, a refrigerated container. And this basically, there's our discharge line from our machine. We go through a vibration eliminator, and we go through this valve arrangement here. And in a defrost mode, we take hot gas up here down this line. We feed it in to, let's say, the expansion valve. In this case, it's got a side port on it. And then we feed hot gas through our, where's my mouse gone, through the evaporator. So we, have a defrost, bring the suction line back, goes through a heat exchanger, goes through a suction accumulator, and then it comes back to the machine. Challenge on what they've done on here is quite good. They've actually taken a tapping off here that puts a little bit of hot gas into the liquid receiver to sort of keep that pressure up, to keep the pressure difference up, so the system keeps running. Now, these evaporators are only fairly small, so they don't take that much defrosting. So it can be done, but it needs to be, the control scheme and all of that needs to be, very, very good. So I'm just going to stop sharing the screen now and go back to the questions. Hope that sort of answered that question a little bit. Okay, so what's that? During heat load calculations, we take fan load, but as evaporator is to be selected after heat load calculations, then how do we assume fan load? There is a sort of generic, we have a cold room heat load calculation in Cool Selector, actually, and hopefully my colleague will put the link for Cool Selector in the chat. But you can generally assume that the wattage of those fan motors for the evaporator, and you can get that as a sort of default load in Cool Selector, or if you know your duty roughly, then find out how many fans you have on the evaporator and take it from there. One thing to say actually, which is important, which is not really about defrost, but please bear in mind, if you have a fan motor in a low temperature room, the air that you're moving is denser. So therefore the load that motor is put upon by moving the air is greater. So the amps that motor draws is greater. And there is a correction factor, I think, that you can add to that, so you can see what the amperage increase is via the lower temperature. So if you're at -10, the amount of amps it's going to draw is different if it's -20. If it's -40, it's going to pull even more amps. So please bear that in mind when you're sizing and selecting the overloads for the fan motors. So Adrian's asking, should checking the fan speed with a light meter worth checking to make sure the speed is accurate, or is that me overthinking? I'd probably say it's overthinking, but things to check with evaporator fan motors are the sort of basic things. Make sure that you are blowing air the correct way across the evaporator. Generally, at least nowadays, we suck through the evaporator. So let's sort of fiddle on my whiteboard. I think I need some new pens, because these are not the greatest in the world. So if we've got our evaporator, we've got our fan motor here, we've got our coil block here. There's our cold room, fabric, let's say, so the air comes in, and we basically do that. So we suck it through the coil. Obviously, we don't want the air going that way, at least in this type of evaporator. Other things to make sure regarding evaporator fans is, yes, make sure the air is going the right way. If it's a three-phase fan, and I've been on site and this has happened, somebody's changed the incoming phases, they don't notice, they still see a fan motor going round, but it's actually going round the wrong way. So check the phase rotation on site, make sure the blade is actually tight on the shaft. Sometimes you'll look up at an evaporator and you'll see maybe, let's say it's got three fans, maybe two of the fans are going around fairly fast, and one fan is just sort of ticking along. And that's when the blade is actually loose on the shaft. So, things like that, most important. One thing to say, just sort of generally about the evaporators, is it's okay. You're stood down. Hopefully you can see my stick man on the floor of the cold room. Yeah, I think you can. We can see this face of the coil, so he can look at that, and he'll look up and he'll say, yeah, it's clear of ice. The problem is there might be an ice build-up on this side of the coil or an ice build-up in the coil. So the best thing to do with a torch is actually shine it through that way and make sure you can see all the way through the coil, and then you know that coil's actually clear of ice. So that's just an aside, really. Okay, another question is, can you please explain how we can do a comparison using Cool Selector to know the impact of refrigerant on simple compression system? We're sort of going off topic a bit, but that's neither here nor there. So I'll answer that one. I don't know whether I've got a slide on that. I can always power up Cool Selector. Maybe we should come back to Cool Selector, but we do have a tool in Cool Selector which is a refrigerant comparison called the Retrofit Tool, and basically you put in your let's say existing refrigerant, your new refrigerant, evaporating temperature, condensing temperature, and it will give you a comparison of that system to say, okay, maybe the compressor capacity will increase or it'll decrease, evaporator capacity might increase, decrease, valve sizes might be too big, too small, things like that. So please go to Cool Selector, and you can find the Retrofit Tool on there. In fact, I do, let me think about that, and I'll try and find it as we go through. So I might come back to that one. So I hope that sort of answers that one. But yeah, please look on Cool Selector, and I'm sure you'll find it. If not, please come back. Grindstone, nice name. What temperature do you recommend for terminating a fan delay? I was always taught sort of -5, -7, and I guess you're talking snap freeze on the evaporator. So around about -5, -7. For those of you who don't know what we're talking about, good idea when you have a defrost cycle is that you have your defrost cycle, you turn your heaters on, you then terminate your defrost either time or on your termination temperature, and then you can have a drip down time, which is important, which I'd always say 5 minutes to drip all the moisture off the fins. Then you start your refrigeration system, and then you can have, not everybody does, but you can have what's called a snap freeze. So you run your refrigeration system, but you don't turn on the evaporator fans. So what that does is it snap freezes any moisture that's left on the coil onto the fins. If we didn't do that, as soon as we turn the fans on, any moisture that was left would blow off the cooler into the store, and that would then build up as frost on the ceiling and the fan guards and things like that. So roughly about -5, -7 is somewhere to start. Okay, so we've got the Danfoss Call Selector link. Adrian says thank you. Okay, unfortunately I can't speak Portuguese, Mr. Tony Turney, so apologies for that. Engineering Mindset asked me a question. Superheat controllers are great for energy savings and also reducing dehumidifications of vegetables. Is there a system or minimum size we should or shouldn't consider for these? Yeah, totally agree regarding superheat controllers. I've been with Danfoss for a lot of years, about 26 years, I think. I'm not trying to give my age away. And for a lot of that time, I actually spent on site working with our electronic expansion valves and controllers. And yep, personally, I love superheat controllers. I think they're brilliant things. So you would use that instead of using a thermostatic expansion valve. You would use an electronic controller and an electrically operated expansion valve, whether that would be a stepper valve or whether it would be a pulsing valve, Danfoss AKV, if any of you know those. They are good at saving energy and also having a very good superheat, controlling the dehumidification, etc. One thing that's sort of worth mentioning is that the expansion valve itself, the only job of the expansion valve is to control superheat. Nothing else. It doesn't control the evaporating temperature, doesn't control the duty, doesn't do anything. It controls superheat. If that's set up correctly, and the rest of your system is set up correctly, then you will achieve the right humidity in your cold room. If it's not set up correctly, then you won't. So what we're also talking about is if we control the suction pressure, we control the evaporating temperature as well, which is very good on a pack system. But when we're talking a one-on-one, one condensed unit, one evaporator, the only way that you control your evaporating temperature is the balance of those two pieces of equipment. And later on this year, I'll be doing some webinars on that as well, and again Q&As after like this. So you ask Engineering Mindset, is there a system or minimum size we should or shouldn't consider for these? Personally, I would say no. We've got electronic or electric expansion valves of many sizes and many different controllers. What I would say is you've also got to think about the cost and also the payback. The other benefit of an electronic expansion valve is that you don't need to worry about low condensing temperature, because the electronic expansion valve can function, let's say, with a lesser pressure drop through the valve than a TXV would. The other thing to say regarding electronic expansion valves is that they have a very good turn-down ratio. So somebody asked a question before regarding blast freeze, blast chill. If you've got, let's say, a blast chill and the duty is 100 kilowatt, and then that goes on to be a holding chill at the end of the cycle, and maybe the heat load or the duty down there is 15 kilowatt. So we've taken, I don't know, let's say hot product straight out of a slaughterhouse or something, and we've got to chill the product right down. So we've got a huge heat load at the beginning and then a fairly small heat load at the end. Electronic expansion valve is very good for that because it can manage the peak duty, but it can also manage the much lower duty much better than a thermostatic expansion valve can. So that's a sort of roundabout answer to the question. So I hope that's okay. Dwayne says the TEV sensing bulb, liquid charge or gas charge on liquid cross charge. Okay, yeah, there are many different types of charges for expansion valves, and they are there to do various things. Let's say that. So we've got the sort of standard charge, which is our range N, which is -40 plus 10, and it can quite happily work in that. Then if you get, you can have much, then you can have other charges which are for much lower temperatures, which are designed for that, and the actual charge and makeup of the charge is different. We've then also got MOP charges. So as I said, if you've got, let's take, for example, a cold room and it has trying to think of an example. Let's say it's storing chickens that are freshly killed, and the heat load is quite high, so the suction pressure goes up. We fit an MOP valve, so that limits the suction pressure coming back to the machine. So we look after our compressor. So they are made up of various charges depending on the application. We've also got things like milk charge, for example, in an expansion valve for milk tanks, and that charge is specifically made for milk tanks, which again have quite a high heat load, but you've got some more technical challenges there as well. So I hope that sort of answers the question, Dwayne, a little bit more. Best thing I could say is take a look at the section for expansion valves, the Danfoss literature, and I'll put a slide up a little bit later on that of where to look, and that will explain all the different charges as well. Okay, so no more questions on the chat at the moment, but I'll keep an eye on that as we sort of go along. So let's go back to the questions that were asked during the webinar. So that's adaptive defrost again. That's the same question. That's delta T, so that's sort of the same question. Somebody asked a question regarding the defrost termination probe. Where is the best place to fit it in the coil? And if I come back to my lovely whiteboard a minute, and do some more fantastic drawings of stickmen maybe. If we think of again, looking at the back of the evaporator, the sort of rule of thumb from the evaporator manufacturers, but also from site experience, is basically, oops, try and write proper, 2/3 up and 1/3 into the coil. So somewhere around about there is normally the start point for your defrost termination probe. Things to bear in mind is if you've got a defrost heater buried in the coil that's sort of there, then don't put your defrost termination probe in that location, because otherwise it'll terminate too quickly. But generally, the cooler manufacturers, space the defrost heaters away from this sort of area, because this is their suggestion: 2/3 and 1/3. Other things to sort of comment really regarding defrost termination sensors is, and I'll do a side-on view now of our cooler. So fantastic fan again, and our coil block with our coils in. Defrost termination sensor, and again, I spend quite a lot of time on site, have done for quite some years. I've seen the defrost termination. Let's say that's the top of the the ceiling. I've seen a defrost termination probe sort of just hanging in midair. Never going to work. It needs to be clipped to the surface of the coil. The way I was taught was basically to actually put it in the coil, so it's sensing the right temperature. Again, the other thing to say is that the defrost termination probe needs to be in the area where the ice lasts the longest. And this is very much site specific, application specific, depending on the airflow across the evaporator. All these sort of things go into that discussion. So yeah, that's as much as sort of can be said. If I could actually tell you the best place to put it and it worked every time, then I'd probably go and do the lottery. But then, yeah, maybe not, because it's a good industry we're in. Okay, what is the right time to start defrost cycle? Again, it sounds like a daft question, but it's actually not a daft question. A famous person once said that there's no such thing as a stupid question, only stupid answers. So for me, any question is always good. If it's a sort of general cold room, freezer room, equally spaced throughout a 24-hour period, 3-4 defrosts a day, 20 minutes, 30 minutes duration each defrost, generally works fine. But then Also, if you've got an application, let's say, of a freezer room, and it's got a lot of use during a particular period, let's say, so if they start work at 7 in the morning and the door to that cold room is open for, I don't know, let's say the next 3 hours, then the door's closed for a period of time, then try and space your defrosts just maybe an hour before the store's due to sort of open and get busy, so the coil's clear. And then at the end of that sort of busy period, maybe 3 hours later, as soon as they shut the door, maybe half an hour afterwards, do a defrost again. Because then all the frost and moisture that's accumulated on the coolers with having that door open is going to get cleared. Maybe make those defrosts slightly longer. Maybe if you can have, generally you have a defrost controller, and it does the same thing on every defrost. Maybe it's a good idea on these very heavy defrosts to actually have a longer defrost time, and maybe a slightly higher defrost termination temperature, things like that, if that can be done within the controller. It's all about keeping those evaporators clear and making them function as best they can, and they'll function best when they're clear of ice and frost. So that sort of tries to answer that one. Is there any defrosting start type sensor? I guess this again comes back to this defrost on demand system that we've got built into the Danfoss controllers in the Adapcool range. In the olden days, I'm old, so in the olden days when I was on site, I sort of preferred to call it defrost skip, because what it actually did was you'd still have your planned defrost a day, maybe 4 defrosts a day, and if it thought it could get away with not doing a defrost, it would skip the defrost. But nowadays, the defrost technology and the algorithms and everything within the controllers has got a lot better, and it now uses the AKV, the controller, and the Danfoss front end as a metering device, let's say, and it works out the amount of refrigeration energy and the air energy, if you like, that goes over the coil. So it uses it as a mass flow meter, and that then becomes a sort of true, do I need a defrost? Yes, no, and then it will do it. So that's the sort of best thing that I know. I have seen various things done on site over the years. I started life at 16 on the fish docks, and there was many ways of doing it. People sometimes just put a thermostat sensor in the coil. When that thermostat sensor got to a certain temperature, it started to defrost. You know, there's various ways of doing it, but I've not seen anything other than what we have in the Danfoss Adapcool controller range. If anybody knows of anything, I'd love to find out a bit more. I'm just looking at the questions on the chat a minute. Okay, great. Thank you very much. Brilliant. Appreciate the good comments. Okay, no more questions on there. Okay, drain line heaters, must they operate all the time? Now, obviously, let's play on the whiteboard a bit more, as we've got the picture of our evaporator up. Let's do the cold room wall a bit better. So we've got our drain off the cooler. So obviously, as we defrost the coil, all the water that we've generated from the ice goes into the drain pan. We've also got a drain pan heater in here, and then if it's a negative temperature room, we should have a heater tape in the drain. Some people wrap them round various ways. Personally, I was always taught to put them internally. Should that be energized 24 hours a day, 7 days a week, or should it only be operated when you're on defrost? Well, officially, if you speak to the cooler manufacturers, it should only be operated when the unit's on defrost, which is fine. Challenge becomes when your drain comes out the other side and you put, let's do a fantastic drawing of a U-trap to trap your water so you don't get any smells, and also vermin actually is quite a good one from the abattoirs that I used to work in years ago. But it also acts as an airlock between outside and this refrigerated space here. You've got minus, I don't know, let's say minus 25 there. And that's not trapped. You get moist air coming up the drain, being pulled by the action of the evaporators, and that causes icing up issues in your evaporator because that moist air carries moisture. So this trap here, if that is in the outside temperature, and let's say it's winter time, and I'll talk the UK, if that's, I don't know, let's say -2, which is a cold day in the UK, that would also need to be heated, but it would need to be heated all the time. So it very much depends on the application and the location of the drains, etc. So that was that one. Then somebody said, can we use adaptive defrosting on controllers for big cold stores? Yes, you can. The functionality of the case controllers that we make with the Danfoss Adapcool controllers, they generally drive AKV valves, and that's a sort of case controller, so it looks after the fans, the defrost, drip down, fan delay, all of that. We will have controllers with a different output for different types of valves, so that's coming. AKVs are fine if it's on a pack system, but one-to-one is a bit of a challenge because of the way the valves function. Other thing to say is that we do have electronic controllers or superheat controllers for large evaporators, and by large I mean large, but the functionality is only the superheat part. It's not the defrost and all of that. But you can use the case controllers. So yeah, please take a chat with your local Danfoss sales office again on that one. A question has come in, and I can't pronounce that name, so apologies for that. What's an oil separator in refrigeration system? Off topic, but yeah, we can answer it. That's what we're here for. Basically, an oil separator in a refrigeration system, it is what it says it is. It separates oil out of the discharge gas and returns it back to the compressor. By the action of the compressor and the the function of the compressor, we move oil out of the compressor crankcase that's entrained in the refrigerant, and it gets pumped out. So the oil sep basically separates the oil out and brings it back to the crankcase where it's needed, because we don't really want oil in the rest of the system. We want it where the compressor is, because that's the function of the oil. It's a lubricating device. Yeah, let's as we've got the whiteboard. If we think of an oil sep in it, sort of, God, that's a bit of a boxy oil sep. That, let's change that one. So yeah, let's think about an oil sep. That's even maybe a bit boxy. We bring our discharge line in. Let's do it nice and simple. And I've got to get this correct. But basically, yeah. So you come in and you go out of your discharge line, and in the oil sep you might have, let's say, some wire mesh or something within the oil sep, and the idea is that as the discharge gas comes in, so that comes from our compressor here, it comes into a space which the speed is actually slowed down, and the oil that's entrained in the hot vapor that's coming in here basically gets caught on the mesh, and it drips down, and then you can have a float at the bottom which opens an orifice which then feeds back to the crankcase. So whenever we get a certain amount of level in the oil sep, the float will open and it will feed our oil back to our crankcase, which is where it's needed. there's many different types of oil separator, but yeah, it is important because we need oil at the compressor, because without oil, our compressor will unfortunately die, which is not a good one. So Stanley's answered my question basically, so thank you very much. Oil shouldn't leave the compressor area. Oil will affect the condensing performance once travel to condenser a lot. Yeah, that's a very good point, Stanley. Oil is an insulator as well as a lubricator, and if it gets in the tubes, in the condenser, it will, let's say, lessen the efficiency of the condenser. One of the biggest challenges, when it gets into the evaporator, it gets cold. And then it gets more thick, and then trying to get that oil back to the compressor can be a challenge. So what we also need to do is that we need to make sure that we've got the right velocity in the suction line that's leaving the evaporator, so that we pull as much of that oil back in the suction vapor as we can, and we can only do that by having the right velocity in those pipes. And yeah, as I said, we want oil in the compressor because that's where it should be. It's doing a job, a very important job. So, okay, let's go back to the questions. What are the pros and cons if we defrost all the evaporators in a room together, or we evaporate them, or we defrost them separately? Good question. Let's just flick back to one of the slides again. So I'll share the screen again. Sorry for jumping about, but this is probably the easiest way to do it. Let's go back to that one. Put that on, and I need to share the right screen. So just bear with me. Let's put that slide up. So hopefully that slide has come up on your screens. Now, one of the sort of challenges is generally, if you've got a cold room with 2 evaporators, 3 evaporators, commercial cold room, as you can see there, the common practice would be to defrost all the evaporators together. Challenge is, if we don't do that, and there's a lot of moisture in the store, as you can see from that picture there, there's a lot of snow on the ceiling of that cold store. And basically what happens is that if we defrost one evaporator and run one evaporator, the running evaporator sucks the moisture that's being generated from the evaporator on defrost, and then it blows it around the room, and obviously the room's cold, so then it frosts on the ceiling. Which might look very nice, but what you've got to remember is under that frost there is ice, and if you get a chunk of ice falling from the ceiling and hitting you on the head, it might hurt a little bit. The downside is if you defrost all the evaporators at the same time, then you get a slightly higher increase in the room temperature. So it is very much dependent on the application, on the goods being stored in the room. If the goods in the room are very sensitive to temperature, and meat is a classic example actually, then you really need to look at the evaporator spacing, fan speed, baffles, all of these things to make sure that we don't sort of cause this to happen. But generally, commercial cold room, let's say at the back of a supermarket, mixed product, generally they just defrost all at the same time. Main thing to say is you've got to make sure that your defrost method, let's say control method, is good, and you're not defrosting too long, because if you defrost too long, then that can also make this snow frosting effect even worse. So yeah, let's hope that was okay. I'll just go back to the video. There we go. Hopefully that's okay. Right, let's look at some more questions. Okay, so we've done oil separator. Sunil asks, in cool selected, TXV need to be selected on 100% capacity or less. what is the meaning of N and B range. Let's talk about N and B range first. That makes reference to the type of charge that's in the valve and the evaporating range that valve can work in. Now, range N is plus 10, minus 40, so it'll happily work anywhere between plus 10 and minus 40 evaporating. And B range, from memory, is a lower evaporating temperature. So it all depends what your evaporating temperature is as to what charge you need. Now, generally, let's say in commercial refrigeration, range N will do everything that we normally do. If you're evaporating at minus 40, then a range N is not really the best choice. You'll need a range B, which minus 40 is sort of not at the extremities of its operating range, let's say. So that's that one. Then we talk about expansion valve capacity. Now, an expansion valve is sized to do a particular duty at a set of conditions. And what I would say, and I've got sort of two hats when I do this. I've got the Danfoss hat, and I've also got the John hat, which is my own personal sort of view on things. And again, it's very application dependent. So if you've got a capacity of 20 kilowatt in a cold room, size your expansion valve to be as close to 80-90% for that duty. That's absolutely fine, because then you've got the pull down part of the valve. So generally when we size a cold room, we always put a little bit extra on, because it might be a warm day one day. So the actual true capacity of the true duty of that cold room might only be I don't know, let's say 17 kilowatts, but we've put a little bit extra on, and we said, okay, let's put the equipment on to do 20 kilowatts, just to make sure that it's going to work when it's a very hot day. So then in normal operation, we might be doing 17 kilowatts. So we don't want the valve to be oversized, because then when we've got this lower capacity, we want the valve still to be able to function properly. So always try and size your valve round about sort of 80%. Duty, absolutely fine. An expansion valve has got roughly about another 15-20% extra capacity on top of the table capacity at the expense of superheat. But yeah, take it about 80% and you'll be absolutely fine. Okay, what is the need of capacity controlling compressor or vapor compression systems? As we sort of said before, and we're covering lots of topics, which is brilliant. I'm going to get a bit hoarse in a minute, and unfortunately I've not got a drink in here, so apologies for that. So if we take it in sort of simple terms, there's our compressor with its piston, and we've got our evaporator. So we come out there, we go through the condenser, we go through our, let's say, expansion device. We've got our evaporator, to make it simple. So that's suction, that's discharge, condenser, evap. Now, the duty of that, if that's, let's keep it simple, 1 kilowatt, then that needs to be 1 kilowatt, roughly speaking. The challenge is, if this is, I don't know, let's say 5 kilowatt, and our evaporator is only 1 kilowatt, then that's too big for that. So we're not going to evaporate at the right temperature. So we need to basically either reduce the speed of our machine, which we can do with a variable speed drive, or we need to reduce some, let's say, capacity. So we could do a hot gas bypass, and we could take a bit of the discharge gas and dump it into the evaporator here, a bit like a hot gas defrost. But we've got to be a little bit careful, because obviously the system is still running, and then we've got to be careful of the temperature coming back to our machine, because we've got to keep an eye on the superheat. So in sort of simple terms, really, it's all about that balance between compressor and evaporator, and they have to match. If they don't match, then you need some form of capacity control to maintain your desired conditions within your system, because whatever system you have, Let's get rid of that, not to make things worse. So let's go back to that. So we've got 1 kilowatt, 1 kilowatt, and that system, you know, all of that is designed to evaporate at, let's say, -5. All of a sudden, if you've got a bigger compressor, instead of evaporating -5, because that's sucking more on the suction, we might evaporate at -10. So what we're trying to do by capacity control is to maintain the suction pressure, suction temperature, the evaporating temperature that we want in our evaporator where we want it. So that's a sort of very simple explanation. I hope that sort of explains what we need to know. Okay, let's have a look. What else have we got? Microchannel coils in the refrigeration system. Dwayne, I think you're asking about microchannel heat exchangers. If you are, yeah, I mean, sort of, the whiteboard's getting a hammer in today. But basically, if we talk about the difference between a microchannel and a fin and tube, in sort of essence, we all know what a fin and tube is. We've got a tube, like so, and we have fins on it, and that's fin and tube. Microchannel, a little bit different, and I've actually got one in here somewhere that I could dig out and show you on the webcam. But basically, with a microchannel, you have a header and another header, and you have a series of tubes, like so. I won't draw all of them. I know, I will. It's tell a lie. And I have to get this right, but basically, let's say the discharge comes in here, and we put a baffle plate. Let's think about it. Baffle plate there, baffle plate there. So, is that right? Yeah, that's right. So our hot gas comes in here. Let's say it goes out there. So that's our liquid. Benefit of a microchannel heat exchanger is that the actual volume that we've got in there is a lot less. So the amount of refrigerant that we need in the system is also a lot less, considerably less. Can be up to 30% less if you compare fin and tube to a microchannel. And if you look at the, let's say, cross-section of the microchannel, and hopefully you can see that, it's basically got lots of holes, lots of tiny holes that the refrigerant passes through. And then between these, let's say, tubes are some pressed fins, sort of like that, that obviously conduct the heat. And we can see there, these are baffle plates that are actually brazed into the header tubes. So the refrigerant flows in like so, da-da-da-da-da, goes in that way, goes through all those tubes, has to go this way because it follows the flow. So it doesn't go through that tube, then that tube, then that tube. It flows through a series of tubes at once, series of tubes like that. And that helps with the pressure drop across it, because obviously if you were coming in here and you fed in that one, then into that one and so forth, then the pressure drop would be way too big. So that sort of difference between fin and tube and microchannel. So hopefully that explains it. Okay, we've got lots and lots and lots of questions, so I'm just going to scroll up a bit and remember where I was. How can ice on compressor confuse during low ref unit? Please explain how much ice is allowed on compressor. Yeah, that's a very good question. I am actually going to be doing some webinars on, let's say, system design, compressor failures, commissioning, all of that. Now, let's do our lovely diagram again. Let's do it this way around. our machine, our piston, ding, 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 expansion valve, our evaporator. So that's discharge, suction, condenser, evap. Nice simple system. I hope you can see that. Yeah, you can see that good. So let's say we are evaporating, I don't know, let's say -5. Now, so we're evaporating -5. Now, with our expansion valve bulb, let's come around here. There's our bulb on our suction line. So we're measuring the superheat on our evaporator. Now, if our suction pressure that we're reading there is, suction temperature is -5, depending on the refrigerant that we're using. Now, if we've got, let's say, if we're evaporating -5 there, and we've got, I don't know, let's say +3 there. So we've got 7 degrees of superheat. And a superheated, what's superheated vapor? Steam is a superheated vapor because it is above its boiling point. So water boils at 100 degrees C. If you measure steam, it's more than 100 degrees C, so it's superheated. So I hope that sort of explains it, because we feed our liquid in to our evaporator through the expanded liquid, and we pass air over that evaporator. The refrigerant that's boiling off in our evaporator is absorbing our heat. So think of that like the kettle. So out of our evaporator, we don't want -5, because if we had -5, we'd have a liquid vapor mix, which we don't want. So we've got +3. We've got 7K superheat there. And then back at our machine, I'm just going to remove that because I don't want to, let's say, confuse. So we've got +3 there. Now, if we had +3 there as well, measured with a probe on our suction stub of our machine, we'd only have 7K superheat. The challenge is you won't get that unless that distance is incredibly short. On a typical installation, if you've got 3 meters of pipe, 10 meters of pipe, 70 meters of pipe, all them sort of strange things that we see, you will always pick up some superheat in that suction line, even though it should be, insulated. We'll still pick up some heat. So we might be, can't read that. +10. So then we've got, let's work that out, we've got 7K suction superheat. So we're picking up a little bit of heat in here, and we're going to make sure that coming back to the machine, it's vapor. What we don't want liquid coming back to our machine, because as I've said before, compressor is a vapor pump, it's not a liquid pump. The challenge is, let's just change some of our figures a minute. Let's say we now, let's make it nice and cold. We're going to evaporate, let's say, -30 C. And apologies for everybody who works in F. Let me check. Yeah, so we're evaporating at -30. Now, if we keep our superheat, let's say, I don't know, let's change it around a little bit. Let's say we've got 5K superheat, which is not a lot, but just to keep the maths nice and simple. So here we'll have -25. Now, the problem is, what you don't want to do is you don't want to have, let's say, +20 here, because then you've got 45K of suction superheat. And our compressor won't cope with that, because that compressor is designed as a low temperature compressor. Now, you might pick up, so we're at -30, -25. We might pick up, let's say, 10K, or let's say 15K superheat. So that means here we're minus 10. So if we're minus 10 there, and it's a nice, moist ambient temperature, we're going to have frost on our suction stub. Doesn't necessarily mean we've got liquid, just means that it's cold. But you only know if it's cold and not liquid by actually measuring your superheat in your evaporator and your suction superheat, or your total superheat, which is that. So that's the way to check if your machine or your system is behaving itself. It's not. I mean, I was taught many years ago. You went to a site and you'd say, "Yeah, the suction pipe's cold, the discharge pipe's warm, and the liquid pipe is, generally sort of ambient or a little bit warmer," and that was fine. But the only way to actually make sure that you've not got liquid coming back to your machine is actually to do these sort of measurements and work out what your superheat is, your evaporator superheat and your suction superheat, because then you'll know whether it is just cold or whether it is actually liquid coming back to the machine. So I hope that explains that one, Sunil. Faisal says recommendations for reducing frost formation in display chillers and freezers in supermarkets. Yeah, that's again very good discussion, and please watch the webinars that I did on defrost. But basically, it's all about ice and frost comes from moisture. So the more moisture there is in the air, the more frost and ice you're going to get on your evaporator. And if that's the case, then you just need to make sure that your defrost mechanism, your control mechanism, your defrost heaters, all of that is working, as it should really. Okay, Stanley's asked a very good question. If 10 evaporators is installed, how many evaporators should go under defrost to still maintain the temperature? There is a general rule of thumb, and I think I mentioned it before. If it's a low temperature room, so freezer room, you need at least 3 evaporators running for every 1 evaporator on defrost. If you're in that's right. If you're in a medium temperature room, so I don't know, maybe it's -5, -6, somewhere around there, then you need at least 2 evaporators running for every 1 evaporator on defrost. So if you stagger it like that, if you've got 10 evaporators installed, I would basically run 9 evaporators and defrost 1, and basically do that through the day. If you can't fit that into a time schedule, then maybe do 2, but it is very much application dependent. What's in the store, what the temperature is, how much temperature increase you can physically have for the product that's within the store. The big freezer rooms that I've worked in over the years, they would generally try and defrost 1 cooler at a time, purely to limit the temperature increase, but also to limit the amount of steam that's generated and moisture that's generated from that evaporator that's on defrost. I think we've answered that question before, Harish. What is the need of capacity control in compressors? So I hope I sort of answered that previously on the slide. If you need to go over that again, watch the recording, and if not, come back and we can go into a little bit more detail. For Success says, dear sir, respected, thank you. Do you have any PDF material to download about refrigeration and air conditioning to know and understand? I'm sure my moderator will put a link on the chat, but we have a lot of information in our sort of area, which is called Cooling United. So there's a lot of PDF material. We've got Danfoss e-learning, which is, as it says, it's e-learning material, totally free to join, available 24/7. You basically sign up, and then you can take as many e-learning courses as possible. We've got loads on refrigeration in many languages as well. Yeah, if my moderator, and I'm sure he's put it down the bottom, there we go, Danfoss School, yeah, training programs. So thank you, Sir John. So yeah, please take a look, because there is a lot of material there as well. Okay. So if there's available in PDF form, it's easier to learn. I don't know the situation regarding PDF, but we do have a lot of material in PDF format. So please take a look through the links that will be put in the chat. And if you, let's say, can't find what you want, then please come back. Okay, Dwayne, which connection of the evaporator during hot gas defrost is optimal for commercial refrigeration systems? And that's from Gregory. It depends what we're talking about, whether we're talking about the simple reverse cycle, whether we're talking about literally putting hot gas into the evaporator on a 1-to-1, or we're talking a 2-pipe system or a 3-pipe system. It all depends. Some people, depending on the type of system, you put the hot gas into the suction, and then it comes back through the evaporator and back down the liquid line. There's so many different ways of doing it, so it's a little bit difficult to say. And sort of what is optimal for commercial refrigeration, that's a bit of a minefield, because you can speak to 10 people and you'll get 10 answers. So I can't really give you what is optimal. I can tell you what is more common, and what is more common is generally the 3-pipe system, where you have a mechanical 3-way valve, and you run a defrost header out to, let's say, if it was a supermarket, for example, you'd run a defrost header out to each branch, and then you'd defrost that branch all at the same time with this 3-way valve. But yeah, there's just so many ways of doing it. So I hope that sort of gives some answer. Okay, how to balance system if evaporator is bigger than condenser compressor capacity? Easiest way really to get your correct evaporating temperature, which is basically what you want in your evaporator. Again, it's very if evaporator is bigger than okay, so yeah, basically just fit an evaporator pressure regulator valve that basically throttles down the amount of suction gas leaving that evaporator. So it artificially keeps the evaporating temperature high. That's the easiest and simplest way to do it. Okay, so and again, for sort of more detailed information on that, please have a look at the Danfoss learning material as well. Okay, I'm just looking at all the other questions. If you're a frigid, get yourself a blood test. Okay, blah blah blah. Something understands easily from Danfoss. I need to know about refrigerator. I haven't. Yeah, so that's fine for success. Sunil, in water-cooled system, how much discharge pressure is allowed? What should be used if customer has available water? What should be used if customer has available water temp 8C instead of 32? Yeah, I mean, obviously, for a water-cooled condenser, Sunil, the colder the water, the better, to be honest, because then you're going to remove much more heat. The challenge with a water-cooled system is obviously water is a scarce commodity. It costs money. So yeah, you just need to make sure that the system is correct. I mean, the discharge pressure should really be in line in what we have within an air-cooled system. It's not so much the pressure. We want to condense that hot gas back to a liquid again. That's what we want to do. So pressure doesn't really come into it. It's all about getting or making sure that we have a column of liquid hitting that expansion valve, that it's not part liquid, part gas, because then we're not going to get the capacity out of the expansion valve. Okay, Robert said he worked for Danfoss for 4 years. Hi, Robert. Stanley says, if under defrost cycle, is it required to install pressure regulators in every evap in the defrost flow? It purely depends. Generally, no, if you have a good defrost system and we're all evaporating at the same time, and again, it depends if we're talking electric or hot gas. But yeah, I mean, if we're talking electric, then definitely no. Yeah, no, it should be fine. What happened if one evaporator fan is running and the other evaporator defrost is on? I think I've sort of covered that, Shiraz, that we get, or you can get this this frosting in the cold room, where the evaporator that's on is drawing the warm, moist air that's being generated by the one on defrost, and it drags it up to the working evaporator and then blows that moisture around the room, which then freezes on the the cold surfaces. Okay, blah, 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 new messages, let's go down to the bottom. Is the electrical defrost heater load included in the total thermal load of the cold room? Generally, no. When you do a cold room calculation, you need to take that into account. There are sort of, general default loads that you can take into account. Please use the cold room selector within Cool Selector, and that will sort of guide you through the process. Shiraz, I think that's the sort of same question, Shiraz, isn't it? Please tell me what happened in freezer room, which has -25 temperature. One evaporator fan is on, and another evaporator defrost is on. I'm not too sure whether you're talking about the fans in the same evaporator or two separate evaporators. But as I said, if one evaporator is on defrost and then a separate evaporator is working, you do run the risk of pulling that moist air from the one that's on defrost onto the one that is operating and then blowing that around the room. So hope that sort of answers that question, Shiraz. Okay, so no more questions on the chat at the moment. Let's go back to the other ones. So we spoke about that. Spoke about that. Defrost termination, done that. Done that. Done that. Somebody asked a fairly good question, actually. It said, what will happen if the defrost mechanism fails? Are there any failure prevention mechanisms that will ensure you don't get ice buildup on the evaporator? Generally, no, I would say. I've certainly not seen any. What I would say generally is that, the cold room operation and the maintenance is incredibly important. And, I've been to, again, quite a few sites where I'll go in and the customer will be saying that we've got a problem with this Danfoss equipment, blah, blah, blah. And the first thing I'll do is I'll go up and I'll look at the evaporator and it'll be covered in ice. Or the fans might not be working, or the defrost heaters might not be functioning, or, there's many reasons. But maintenance is, for me, a really good thing, and it needs to be done. But also cold store operation needs to be thought about. So airflow across the coolers, all of that, door control, they're very, very important to make sure that your defrost functionality works as it should, and therefore the refrigeration system works as it should as well. So that's sort of all the questions that I've got from the seminars. We've actually covered quite a lot on the chat as well. If there's any more questions, then please put them up. If not, then I guess we call it a day and we wait for my next one. So I'll just give it 2 minutes. Thanks, Robert, for your comment. Yeah, I appreciate that. It's different topics. So Sunil asks a question: blend refrigerant can be typed up or not? Topped up. Um, yeah, there's been a lot of sort of discussions about blended refrigerants, and if you have a leak, do you then need to reclaim the whole charge and then put a fresh charge in? And basically, the sort of outcome was that actually, no, you're fine. But I think that depended on how much of the charge you'd lost. I think it sort of, I think if it was less than half the charge, you were generally okay to top it up again. But if you'd lost greater than half, then really you should reclaim and fill up with a brand new charge. But yeah, that's an interesting question, I have to say. Stanley's asked quite a detailed question on hot gas. Is there a two-step valve that is used? Yes, there is. How long is the interval from the first stage to the second stage? I can't tell you off the top of my head, Stanley. But yeah, we do two-stage valves, and the reason we do these two-stage valves is to avoid this thermal shock. What we don't want to do is open up a valve instantly and allow all this hot gas to rush into the cooler, because that thermal shock can cause vibration, it can cause fracture, and in a lot of cases, it's led to fracture, and particularly when we talk about ammonia systems, even CO2 systems, that can be incredibly dangerous. So if you are using hot gas on an industrial system, then please make sure that you've got two-stage opening valves or slow opening valves. But sorry, Stanley, I can't tell you that sort of stage without looking at a document, so apologies for that. Okay, lovely. All right, so I don't think there's any more questions. Hope that was okay. Hope the format is okay. I know we jumped about a little bit between the whiteboard, the video, the screen, and so forth. But yeah, that seems to be the way that I can do it. So apologies for that. And yeah, if that's it, thank you very much, and we'll see you again soon. Bye for now.